Okay, so welcome again for another video lecture session for integral calculus. So today's discussion would be on trigonometric integrals. So for today's discussion, we will be needing the following list of identities, Pythagorean identities, and power reduction formulas in order to perform the corresponding techniques of integration. Okay, so for the first item, we need to have the list for the Pythagorean identities. Of course, for this topic, I assume that you already know at this point the corresponding identities from your trigonometry. So, okay, so for this list, we have the Pythagorean identities. We have sine square x plus cosine square x is equal to 1. Also, we have tangent square x equals secant square x minus 1. Cotangent square x is equal to cosecant square x minus 1. Okay, so also we have here the power reduction formulas. These power reduction formulas are those identities that connects the double angle formula for cosine. So what we have here is cosine 2x. This is a double angle formula and connects it with corresponding formulation equal to the sine of the square of the sine square of the given angle x. Also, we have of the form 1 plus cosine 2x over 2 for cosine square x. So alternatively, we can have sine square x to be equal to either 1 minus cosine 2x over 2 as one of the form for making use of the power reduction formulas, or simply we can have sine square x solved here. Now, we can do those alternate forms for sine square x depending on the need in the solution of the integrals. Okay, so also for cosine, we could either solve for cosine square x from the Pythagorean identity formula, or we can simply make use of the form of cosine square x in the form of 1 plus cosine 2x over 2, making use of the double angle formula. Okay, so we call this set as the power reduction formulas. We call this set as the Pythagorean identities. Also, for this topic, we need to have the list of the derivatives and the corresponding integrals that we already know regarding trigonometric functions. Okay, so in the list of our derivatives, we already know this part. Derivatives of each of the individual trigonometric functions. So we have derivative of sine, derivative of cosine, derivative of tangent, derivative of cotangent, derivative of secant, and derivative of cosecant. Okay, so the corresponding results would be derivative of sine is cosine, derivative of cosine is negative sine x dx, derivative of tangent x is secant square x dx, derivative of cotangent is negative cosecant square x dx, derivative of secant x is secant x tangent x, and finally we have derivative of cosecant x equal to negative cosecant x cotangent x dx. Also, the reverse formulation for getting the antiderivative of each of these results, we have the integral of cosine x dx results to sine x plus c. The integral of sine x gives us negative cosine x then plus c. The integral of secant square x gives us tangent x plus c. Integral of cosecant square x is negative cotangent x then plus c. Then the integral of secant x tangent x, we have secant x then plus c. And the integral of cosecant x cotangent x dx gives us negative cosecant x plus c. Also, we will be including in this list the complete set for the integral of the 6 trigonometric functions. So we have already in the list the integral of cosine and in the integral of sine. So what is missing here is the other 4 trigonometric functions. So we have we'll be including in this list the integral of tangent x dx, so that gives us equal to ln of secant x plus c. Integral of secant x dx as ln of secant x plus tangent x plus c. Integral of cosecant x dx gives us negative ln of cosecant x cotangent x. And finally, we have integral of cotangent x dx equal to ln of sine x plus c. Okay, so if you remember from the previous video lecture on trigonometric integrals, techniques of integration, I ask you to answer or to solve for the corresponding result for integral of cosecant x dx and cotangent x dx, but so far none of you has submitted, so I'm still waiting for your submission for the proof of solving for the integral of cosecant x. This is the result, and the integral of cotangent x dx, this is the result. Now, what I suggested is that you will make use of Wolfram alpha in order to be guided with the corresponding derivation of these results. But remember, the use of Wolfram alpha, just like I have suggested, you will be using Wolfram alpha as a tool, but more importantly is the mastery of the maturity in mathematics is the more important point in our discussion. Okay, so knowing this, I will now be proceeding with the trigonometric integrals. Remember, this is the topic in our discussion regarding techniques of integration. So for this topic, trigonometric integrals involves the different forms of the powers of the trigonometric functions sine, cosine, and tangent. So whenever, as we can see here, there are forms of the trigonometric functions that has exponents in them, such as secant square, cosecant square. How about the case wherein we have, for example, integral of sine square x dx or integral of cosine cube x dx? So what would be the corresponding results of those integrals? So that is our topic discussion for this video lecture. Okay, so we will be breaking down those scenarios into cases wherein we will be dealing with the powers of sine and cosine, the powers of when the power of sine and cosine is is when the power is a positive odd integer. Another case is when the powers of sine and cosine is a positive even integer. And the third case is when the tangent of the power of the tangent is an integer also. Okay, so let's talk about case 1. Case 1 is you have the integral of sine raised to mx dx or integral of cosine mx dx, where m is a positive odd integer. Okay, so let's consider example number 1. We have integral of cosine cube x dx. So what we have here is that you have the integral of cosine raised to a power that is an odd integer. Okay, so the corresponding technique goes like this. What we need to do as an initial step is to separate your cosine cube into two factors. One of the factor of which is the base form of the trigonometric function, which is cosine x. Of course, when you separate cosine cube x into two factors, in which one of them is the base, so what you need to do with the other factor is simply 1 degree is only 1 degree lower. So if you have cube here, so that the factor should be separated into cosine square x and cosine x. Now, from the introduction of the factors of cosine cube, we have cosine square x and cosine x. Next step to do is to replace your cosine square x by one of the trigonometric identities that is presented here. So obviously, we can solve for cosine square x by transposing sine square x to the other side, the side of 1. So what happens here is that cosine square x becomes 1 minus sine square x. So doing that, replacing cosine square x in the integrand, so we have 1 minus sine square x multiplied by cosine x dx. So from here, we will be having two terms, obviously, distributing the integral sine and cosine x dx to both 1 and negative sine square x. Okay, so doing that, we have this would be cosine x dx times 1, so this becomes integral of cosine x dx minus This becomes, the next term becomes integral of sine square x cosine x dx. Okay, so from here, we need to realize that the solution that corresponds for the second part of the integral is, we make use of the substitution or representation of letting u equal to sine x, or the base of sine square x, which is sine x. So let u equal to sine x, realizing that the du is equal to cosine x dx. So from here, if we let u equal to sine x, then sine square x becomes u square, and cosine x dx becomes our du. So therefore, this second form of the integrand becomes negative integral of u squared du. While the first part of the integrand already has a solution, so integral of cosine x dx is equal to sine x. So what is left now here for us to perform the integral of u squared du, making use of the power formula. So from here, sine x minus integral of u squared du becomes sine x minus 1/3 u cubed, then plus c. Okay, so replacing back the value of u, or the representation of u is equal to sine x, so that becomes u cubed, or sine cube x, then plus c. Okay, so finally we have the answer for the integral of cosine cube x dx equal to sine x minus 1/3 sine cube x, then plus c. Now, take note that whenever we encounter the form of the integral of this form, meaning we have the integral of cosine or sine in the form that has the power equal to a negative integer, we can always perform this method of separating your given trigonometric function with power into two factors, one of which is its base form, and the other one would be left with a power that is raised to an even integer. Now, of course, once it is even, that means we could make use of the trigonometric identities presented above in order to replace the form of the trigonometric function with an even integer. Okay, so let's try another example. Okay, so we have here number 2, we have integral of sine raised to 5x dx. Okay, so doing the suggested solution, so the first step in performing this integral is to separate again the base form of the function sine from our original given sine raised to 5. So doing that, we have sine x dx, and what is left in our original power for sine is sine raised to 4. Of course, sine raised to 4 can be factored further into sine square x square, so that is sine raised to 4. Now, so from here we have now the form of sine square x. So from here we can now replace sine square x with the Pythagorean identity, solving for sine square x. That would be 1 minus cosine square x. So from there we can replace sine square x. So what is left here is that we have 1 minus cosine square x square times sine x dx. Okay, so expanding first the binomial 1 cosine square x gives us 1 minus 2 cosine square x plus cosine raised to 4x, then times sine x dx outside. Okay, so since we will now have the expanded form of the integrand, the next step is to distribute the integral sign and sine x dx to each of the terms in the expanded form of the binomial. So from here we have sine x dx times 1 integral, so that becomes integral of sine x dx. The middle term would be negative 2 integral of cosine x square sine x dx, and the last term would be integral of cosine raised to 4 x sine x dx. Okay, so as illustrated in example number 1, the next step is to let u equal to the base function of cosine, so that becomes let u equal to cosine x, realizing that du is equal to negative sine x dx. Okay, so replacing cosine square x with u, that becomes u square, and sine x dx is equal to negative du. So that becomes negative 2. That becomes positive 2. So this becomes 2 integral of u squared du. Applying the same substitution for the third integral, so we have cosine as our u, then cosine raised to 4 becomes u raised to 4. Now sine x dx is negative du, so this is positive, so this becomes negative integral of u raised to 4 du. Now of course what is left here, the first integral of course has its solution already, so we have integral of sine x dx as negative cosine x. So what is left now in using the power formula is for the last two integrals. So we have negative sine x. Okay, so this becomes negative cosine okay, so negative cosine x plus, using the power formula for u squared, this becomes u raised to 3 over 3. Since there we have 2 outside of the integral, so this becomes 2/3 u raised to 3. Now for the third integral, we have u raised to 4. This becomes u raised to 4 plus 1, or u raised to 5 over 5. So this becomes negative 1 over 5 u raised to 5, then plus c. Okay, so correspondingly, replacing u with our original substitution of cosine x, this becomes negative cosine x plus 2/3 cosine cube x plus, or this becomes minus. Okay, so this becomes minus 1/5 cosine raised to 5x, then plus c. Okay. Okay, so let's proceed with case number 2. Okay, so case number 2 is still you have the form of integral of sine x dx and integral of cosine x dx, but this time the powers for sine x and cosine x is an even integer, a positive even integer. Okay, so let's consider integral of cosine square x dx. Of course, it would be no use if we're going to replace immediately cosine square x with 1 minus sine square x. That would be simply a redundancy of the process of replacing the squared form of the trigonometric function with another squared form of the trigonometric function. So alternatively, we can replace cosine square x with the replacement of the other form, making use of the reduction formulas. Okay, so the reduction formulas for cosine square x is equal to 1 plus cosine 2x over 2, making use of the double angle formula. Okay, so making use of the reduction formula, so we have integral of cosine square x dx as equal to integral of 1 minus cosine 2x over 2 dx. Now notice, since we have our numerator as a binomial, we could separate actually the fractions into two separate fractions. One we have integral of 1 over 2 dx, and the other one is 1/2 integral of cosine 2x dx. So from here, of course, 1/2 integral of dx has already its solution. So we have 1/2 1/2 x for the solution for integral of dx. As for the second part of the integrand, we can first represent 2x as equal to u, since 2x represents the angle for cosine. So we can let u equal to 2x. du would be 2 dx. Solving for dx, we have du over 2. Now, replacing cosine 2x with cosine u and dx as du over 2, this becomes du over 2, so we have a constant 1/2 that would appear here in the integrand. Of course, what we do with the constant is we place it outside of the integral sign, so there is also 1/2 outside the integral. So the two 1/2s will be multiplied to each other, so this becomes 1/2 times 1/2, that becomes 1/4. So what appears here is we have 1/4 integral of cosine u du. Okay, so of course, we already have the solution for integral of cosine u du. The integral of cosine u becomes sine u. So we have now 1/4 sine u, then plus c. Okay, so replacing u with our substitution as equal to 2x. So this becomes 1/2 x plus 1/4 sine 2x, then plus c. This will be the solution for integral of cosine square x dx. Okay, so let's have example number 2. Okay, so we have integral of sine raised to 4 x dx. Okay, so as illustrated above, what we can do with sine raised to 4 x dx is to replace sine raised to 4 by sine square x squared dx. So again, it would be nonsense it would be a redundant solution if we're going to replace sine square x with a simple substitution from the Pythagorean identity. So what we can do as an alternate solution is to make use of the power reduction formula, replacing sine square x with the form of 1 minus cosine 2x over 2. Okay, so that is squared, so meaning we're going to square this whole term. So square of 2 gives you 1/4, so we can the square of 1/2 gives us 1/4, so we can actually place 1/4 outside of the integral. That is why we have 1/4 here. Now, what is left in the integrand is the solution for the square of 1 minus cosine 2x. Of course, this is a binomial, so we'll be performing the square of the binomial. Okay, so the square of the binomial in its expanded form, we have 1 minus 2 cosine 2x plus cosine square 2x then dx. Okay, so this is simply the distribution of 1/4, the integral, and dx to the three terms in our integrand. Okay, so we have 1/4 integral of dx. The second term, we have 1/4 times 2, so that becomes negative 1/2. So what is left here is negative 1/2 integral of cosine 2x dx. Next is we have 1/4 integral of cosine square 2x dx. Okay, so at this point we can now perform the integral of 1/4 integral of dx. Of course, that becomes 1/4 x. So that is why we have here 1/4 x. Now for the remaining two integrals, we represent first. We let u equal to 2x. Now du of course is 2dx, and dx is equal to du over 2. Okay, so replacing 2x with u, that becomes cosine u, and dx with du over 2, so that this becomes du over 2 times we have 1/2 outside, so that becomes negative 1/4 plus this becomes cosine square u du over 2 multiplied by 1/4 outside, that becomes 1 over 8. Okay, so simplifying further, we have 1/4 x minus integral of cosine is of course sine. This becomes negative 1/4 sine u. Now for cosine square u, remember we already have the form of the integral of cosine square u du. We already have this as our example number 1 for this case. So the form of integral of cosine square x dx gives us 1/2 x plus 1/4 sine 2x. So meaning, if we have cosine square u, this becomes 1/2 u plus 1/4 sine 2u, then plus c. Remember that this form, cosine square u, is the one that we have presented as example number 1. So we just replace u with x. Okay, so now, what is left here is the further simplification. Of course, this becomes 1/4 x minus 1/4 sine u. Distributing 1/8 to the two terms for the result of the integral of cosine square u du, this becomes 1 over 16. Okay, so u becomes 2x. 1/4 sine 2u, 2 times 2x becomes 4x. And we also have 1/4 times 1 over 8, that gives us 1 over 32. Now, of course, 1/16 times 2x gives us 1 over 8. 1 over 8 plus 1 over 4, 1/4 plus 1, 8 gives us 3 over 8. Now, minus 1/4 sine 2x. And finally, 1 over 32 sine 4x. Then plus c. Okay, so this would be our final answer for integral of sine raised to 4x dx. Okay, so last for our topic discussion, we have case number 3. This time for the form of the tangent, power of tangent, the integral of the power of tangent x dx. Okay, so where n is a positive integer. Okay, so n here is simply a positive integer regardless whether it is positive or negative. Okay, so let's take example number 1. Integral of tangent cube x dx. Okay, so what is presented here is that just like in case number 1, whenever we have the power of the trigonometric function in odd form, or it is the power is given as an odd integer, so we can apply actually the technique that was presented in case number 1. So meaning we're going to separate the tangent cube into two factors. One factor of which is the base form, which is tangent x, and the other factor would be the remaining power for the resulting power of the tangent. So in this case, tangent cube minus 1 gives us tangent square x. Okay, so from this step, just like what is presented in case number 1, the form of the tangent square can be replaced by the form of tangent square in the Pythagorean identity. Of course, in our Pythagorean identity, tangent square is replaced by secant square x minus 1. Okay, so replacing tangent square with secant square minus 1, so this becomes secant square x minus 1 times tangent x dx. Okay, so next step is to distribute. So we have now tangent x secant square x dx minus integral of tangent x dx. Of course, we already have a solution for negative tangent x dx. This is one of the basic formulas that was presented above. So the integral of tangent x dx gives us negative ln of secant x then plus c. Now what is left here for the first part of the integral is simply the integral of tangent x secant x square x dx. So for this part, we let u equal to tangent x, realizing that du is equal to secant square x. So therefore, if tangent x is equal to u, secant square x dx is equal to du. So the form of integral of tangent x secant square x is actually in the form of integral of u du, which we can solve using the power formula. Of course, using the power formula, this becomes u raised to 1 plus 1 over 1 plus 1, or that becomes 1/2 u raised to 2 plus this could be left as negative ln of secant x, or simply by the properties of the logarithm, if you have a negative if the logarithm is preceded by a negative sign, the negative sign can be placed inside the value of the logarithmic function as an exponent. So if this is negative 1, so this becomes secant x raised to negative 1, or simply the reciprocal of secant x, which is cosine x. Okay, so finally we can replace u with our original replacement of tangent. So this becomes tangent square x plus ln 1/2 tangent square x plus ln of cosine x then plus c. Okay, so that is the topic for trigonometric integrals. So I am expecting that you will be answering the following exercises. You could simply pattern the solution for each of these numbers based on the solution that were presented in the corresponding examples above.